see if I can remember how to do the screen recording thing. It will record the microphone. Cool. We wanted to take it back. Great. That should be working now. Cool. So my name is Claus. I work here at Humi. I mostly work on the payroll part of this application. And we're not really going to talk about that today. This is just a platform where I can do more of my propaganda about network stuff, but we are of course going to do it with Ruby. But I was gracefully allowed to talk here today, so that's great. So we're going to do IPv6, which some of you might know what is, some of you might not. We'll do it for fun and profit, but we'll do the profit first, which is all the boring business stuff, and then we'll do the fun part after where I try stuff live, and it will probably break because that's always how it is when we do stuff live. Are you cool with that?
Yeah.
Cool. Great. So this is me. I'm Claus Lensbøl. That's really hard to pronounce. I'm from Denmark. I have a master's degree from the Technical University of Denmark in telecommunication, hence why we're talking about network. I have a background in developing stuff that is embedded and for network. I've been working on network testers and IoT devices for home and a bunch of those things. And this is interesting. Okay, it came back. Cool. So yeah, that is kind of my background. If you want to ask me stuff about this talk after this, you can find me. I'm sure Simon will also put stuff out. So just text me and ask. So what is the internet? Let's start with the big question. So most of you have very limited access or what do you call it? Interaction with the internet, or like in the how does things work. And that's great because it means that things work. When you interact with the internet, that's because something is broken, you restart your router, all that stuff. But in reality, the internet is not just one network, it is a bunch of networks. It is Telus, it is Bell, it is Rogers, it is all the other crooks. And they're kind of, on the big grand scheme of things, they're kind of their own kind of small cloud, and then between these small clouds, there's a network as well. So we call it a network of networks. So Telus has a bunch of stuff that's proprietary to them. We don't know about that, but we can traverse their network, and then we can get to somewhere that's better, or our destination, or whatever we call it. It's also the network that's built on trust. So when we say, hey, I have these addresses over here, we mostly just trust that, which is mostly great, but sometimes some countries have a tendency to be a bit like, hey, we're actually hosting 8.8.8.8, which is Google's DNS. And when that happens, a bunch of shit goes down, and people are not happy. So there's trust, and people are trying to move away from some of these trust models, but that's how it is right today. It's also a hierarchy of protocols.
What is 8:30?
8:30, cool. It's there's a hierarchy of protocols. So that means that whenever you have a web request you send to someone, you have a small piece of text. And then you take that small piece of text and you wrap it in something else. And then we take that something else and we wrap it in something else. And then we take that something else and we wrap it in something else again. So there's all these layers outside of that small piece of text that you're creating. These would be a TCP UDP header, it's a MAC address header and footer, and it's whatever happening on the physical medium, which might be with error-corrected codes over Wi-Fi, it might be different kind of modulation on the fiber. Totally not relevant. The important part is that whenever you make your small requests, you make your GET request to someone, your GET request gets all the way through the stack and gets wrapped in all these different things and go over 8 different networks and God knows where, and then it gets unwrapped again on the other end to get you that get index dot whatever, and then the whole thing happens in reverse to get all your data back the other way. That's the basics of it. We're not going to go into more details about that, but that's going to be relevant later. We have 2 main protocols that we use. Hopefully, some of you have seen these terms before, TCP and UDP. TCP is a connection tracking protocol, so you have retransmissions. You have stuff like, hey, I got packet 4 before I got packet 2. So the protocol, the OS stack will nicely reorder them for you and give them to you in the right order. And it has all that kind of stuff, but it also has a bit larger overhead, and it is prone to also have issues like head of line blocking and a bunch of other stuff. HTTP in versions 1 and 2 uses TCP, and SSH and SMTP and IMAP, which are the email protocols, uses TCP. On the other hand, we have UDP, which is just, hey, here's some data, fetch. And then you just have to kind of see what you get, and if you get it, that's great, and if you don't get it, who cares? If you get things out of order, that's your job to figure out, but it also doesn't have a ton of overhead. So it's really good for streaming of data, so if you're watching a video stream, you really only care about the newest frame, you don't really care about the last many frames if you're watching something live, so if you drop 20 frames, who cares? I just want the newest one. HTTP 3 is actually being built on UDP, which means that Quick, which is that protocol that they're doing, just re-implements all the things from TCP, but in UDP to avoid some problems with TCP. It's a bit weird, but soon a lot of the traffic will be UDP instead on the internet. Also, DNS uses UDP and SIP, which is stuff like calls, like phone calls over the internet. Cool. We're getting over this fast. There's two internets. There's the old one, that's the IPv4 internet. It was developed back in the 70s and a bit before. They were like, yeah, 32-bit of addresses, 4.2 billion addresses, that would be plenty. It wasn't. They also gave like something like 1/8 of the 256th of the internet to just Ford. So just the Ford Motor Companies, they're just like, here's the 256th of the entire internet. They just got that. So that has had a ton of issues. There's a way we notate it, but you've seen these addresses before, right? Maybe you've seen 192.168. Blah, blah, blah. This is the same, it's a private address. Don't really care about that thing. This is the old. This is just what it is. It has some problems. First of all, in North America, we ran out of addresses in 2015. So in the past 9 years, the prices have gone steadily up of IPv4. So if you want to buy IPv4, you're currently paying around $45 to $6 per address. If you're a new ISP trying to come into the world, which I know is a shocking thought in Canada, but if you were a new ISP trying to come into the world and you wanted to buy some IPv4, you would be out of money before you even started. That's not great. If you're on AWS, every IP address costs you about $45 US a year. They're probably going to jack up that price at some point, but right now that's what IPv4 costs at AWS. They spend billions of dollars buying up addresses from other people, so now they're getting that back from you, and we're getting that back from the customer, and so on and so forth. There's also a bunch of things like network address translation that makes it hard and makes things, it just adds latency. We get tons of stuff where we have to translate between different networks because we're running out of addresses, so it's not fast. Also, it's not super relevant for us, but it's really hard to make direct connections, but if you're trying to write video games or whatever, that can be interesting. Cool. This is the new thing. Yay! The new thing is called IPv6. Instead of having 32 bits of addresses, we have 128 bits of addresses. So we have this many addresses. And I'm not even going to try to, I think it's, is it 340 on decillion? I don't know. It's a big number. There's enough addresses. That's the general gist of this. Yes? This is interesting. Okay. There's enough addresses. We don't really need to worry about that part of IPv6. Can anyone here tell me what they think the IPv6 usage in Canada is? We'll give it to the front here.
I'm guessing 25%.
Okay, other guesses?
7%.
7.
2.
2.
I was going to say 33.
33? Getting warmer? Okay. Yeah. So what?
80.
Oh, that would be great. We're around 40%. 40.6. I took the screenshot the other day. Today it's actually closer to 41%. So it's getting up there. And we can see the graph of the thing over there. That's fine. But around 40%. So that means that if you are not serving IPv6 on your web app or whatever you're hosting, around 40% of your customers are having 10 milliseconds of latency more on their request to you than if you had your app on IPv6. Think about that. Cool. Advantages, lower latency 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 this is actually the key in the profit part. Because what does lower latency mean? That means better SEO. Google says that if your website loads faster, and if your website is on IPv6, it will put you on higher rankings. So it's free SEO. Here you go. This is the for-profit part. If you didn't want to see anything fun, this is where you can leave. Cool. IPv6 equals money. It's also more or less free because we have an ungodly amount of addresses, and the protocol is simpler for the hardware to parse because a lot of it has happened since the 70s, and even though IPv6 was designed and standardized in 1998, 26 years ago, that's wild. It's still way easier for hardware to parse. Cool. Also, if you have a client that does, like a mobile client, for example, you have your mobile phone and you are, let's say, on AT&T as a client. Maybe you have clients that are in the States and they're on AT&T. AT&T doesn't give any IPv4 addresses to their users. They only give IPv6 addresses to them. That means that if your AT&T client needs to contact your website or GitHub in this situation, we have this long dance of the client asks a cheating translation DNS server, hey, where's github.com? GitHub, the translation thing asks GitHub and gets the real address. Then we have to translate that into this fake address that starts with 64, which is this weird translation address that we can send data to. Then our client sends that weird translation address to say, hey, I'm pretty sure GitHub is this way, so I'm going to send this up to our router that is a net64 router. And then that gets translated into IPv4, and then all the way back again. And like, that's a lot, and that's a lot for one call. But then imagine you have a website, and yeah, sure, the whole DNS thing doesn't happen for every call, but then you're fetching a couple of assets from another server, and you're fetching maybe some JavaScript, or you're calling something else. Then that happens every time. That's a lot of latency. You don't want that on your connection. So especially for mobile clients, IPv6 on your app is really good. Cool. Some myths before we get into the fun part. People says that no NAT is like no security. NAT is not security. If you know what NAT means and you have thought this, how many thought that NAT was security? Let's start with that. Did anyone think that? Cool. No one cared. Great. There's weird no, that's perfect. There's weird attacks where companies like eBay can scan your local network. So when you go to the eBay website, eBay will actually use JavaScript to scan your local network. It's pretty creepy. A lot of companies are doing it. You can also do net slipstream and tagnet. Super not relevant. Myth number 2, you can be tracked everywhere. In the beginning, when they did IPv6, when your computer got an IPv6 address, just slap the MAC address of your computer, which is a fixed hardware address, on the end of the address. So when I was on one network, the front of the IPv6 address would be one thing, but the tail part would always be the same. So for advertisers, they're like, oh yeah, we like that. But we don't personally like that. So they fixed that in 2007 and then later in 2014. So we're over that problem. And last, they're like, oh, we don't need to support IPv6. We have plenty of IPv4, and no one uses it. And then see rest of presentation why that's not true. Okay. Cool. So do you have IPv6? This is a QR code that goes to that website. You can check on your phones. If you don't trust the QR code, you can type it in instead. But I promise I didn't do weird stuff here. Green? Red? Nothing? Did you crash?
Crash.
Is that one green? Yeah, we got one green over there. Are you on Rogers?
Yeah.
Yeah, cool.
Green.
Green, you're also on Rogers?
Tell us.
Tell us. Ooh, that's new.
Humi Wi-Fi.
Yeah, Humi Wi-Fi. Cool. Beanfield. Weird, it's not loading for you. Oh, that sucks.
Tell us.
Oh, cool. Yeah, so tell us is not even consistent. Some tell us green, some tell us red. Cool.
Someone get IPv4.
All right. So for the first part, IPv4 is expensive and it's slower than IPv6. IPv6 is faster than IPv4. It's free and it's good for your SEO. So that's the end of the profit part. That's the boring part. Now we can get to the fun. Okay, cool. So now we're just going to do demos and we're just going to be looking at code.
Oh no.
Yeah. Oh no, code. Looked at that all day. Oh, no.
Unicast.
Let's do here. Is this big enough, or do you want it larger fonts?
I think it's big enough.
Looks good.
Cool. Great. Okay, let's start with a TCP server. Have anyone ever written a socket program in Ruby before? 1, 2. That was 2. Wow, cool. So this will be your first. Well, you can do it when you get home. But when you get home, this will be your first socket program. Normally, you have seen socket programs. They will say, "Oh, we need to listen on some address," and a lot of places will just say, "Hey, listen on empty string." Empty string means listen on everything on IPv4. If we want to listen on everything, both IPv4 and IPv6, we just put : : Then suddenly we have these magic sockets that we will talk about in a second that listens on both IPv4 and IPv6. Cool. Then we listen on some port. I took 1, 2, 3, 4 because I'm really, I don't know. I took 1, 2, 3, 4. And then we'll make a server socket, which is just TCP server.view. This is all standard in the socket library. We give it a listen address and a port, and then we just loop over whatever connections we get. So the client socket is the server socket.accept, so we accept new connections coming into us. At this point in time, we could go back and do the outer loop again, but I'm lazy at this point in time. We can figure out what the client is connecting from. So this is the thing. If you have a WebSocket, or like a socket, not a WebSocket, but a socket that is listening on both IPv4 and IPv6, how do you know, and how does the remote address look like in this socket? Well, what happens inside of your operating system is that it says, hey, we just represent everything as IPv6. So what it does is that it takes a specific IPv6 address, and then it just slaps the IPv4 address at the end of it. So whatever you want to save, you can just save that. So if you are tracking IP addresses in your database, which is a bad idea, you can just save that 128-bit field. If you are trying to do other logging, or you're trying to figure out what's happening there, you have it all as IPv6. So just treat everything as if it were IPv6. So for your perspective, even if you don't have IPv6 on your app, and you don't have, for whatever reason, all that stuff, you can go out and deploy that now and just say, hey, I want a dual stack socket. That works on every operating system except for OpenBSD for reasons. Don't even want to get into it. Something, they said security, everyone argued with them, and then they were OpenBSD, so they didn't care that everyone argued with them. Yeah, so we get this magic thing for free. Even if we didn't have IPv6, we could still listen on it. We would still be ready for whenever that network transition has been done. Then we'll write back to the client, and we'll close the socket, and we'll do it again. So let's try this thing out, shouldn't we? Nope, don't do smileys. So what we're gonna do is not do that, but we're gonna do that. No, yes. So we're gonna do our Ruby TCP socket, server, RV, and then we're gonna go down here, start a new terminal, and we're gonna use a tool called NC. It stands for netcat, so it's kind of like cat if you ever use cat, but it just does it on the network instead. We're gonna connect to localhost. Whoa, that also messed up my thing here. And we're gonna connect to localhost at port 12345. Does this make sense so far to most people? If it does not make sense, scream out. I don't know why this, the projector flickers, that does not make sense. So if I do this now, it says, hey, a client connected from : 1, which is a localhost, using IPv6, and then we can write something to the server, and then it will write it back to us and say, hey, you connected via IPv6. What happens is that our system says, I need to get to localhost. And then, netcat says, I need to go to localhost. And the Mac in this situation, but your Windows PC or your Linux PC will say, where is localhost? It will make a DNS lookup, which is go to the most likely the host file in the system, but it will figure out where is localhost. And it will figure out how to connect to localhost. There is something that is built into most operating systems now that's called happy eyeballs. It's a thing that says, hey, this host could be available on IPv4, or it could be available on IPv6. I'm going to connect to both, and then I'm just going to figure out which one responds fastest, and I'm going to use that one. Newer version of Happy Eyeballs will even accept that IPv6 is a bit slower, but as we've seen, that's rarely the case, so that's not really a problem. But it will generally prefer IPv6. And as it does here, if we put a -4 in here to connect via IPv4, we would see this weird IPv4 address with : FFF in front of it. And this is the weird, we take an IPv4 address and pack it into an IPv6 address, and then everything is cool. Okay, so far so good. Anyone feels like this is weird, strange? Everyone's following along, cool. We also have a, we also have a TCP client. Just for the sake of it, it basically just opens the socket to an address and a port. It says that it connected to it, it writes stuff into the socket, and then it closes itself. Very simple. Run the server. I don't know why that crashed, that's weird. And it's going in server. And this thing will just connect, and that's what we saw before, right? Nothing magical here. This is whenever you connect to a server and you try to scrape something, you hit an API. This is basically what's happening in Ruby underneath. So it goes through the whole network stack, and somewhere in HTTP or in whatever library you're using, this is the stuff that's underneath. Cool. Especially if you haven't tried that before, that's something new. So now you heard about TCP, but what about UDP that we talked about before? We're slowly stepping towards more advanced stuff. So let's look at a UDP server. This looks awfully like what we saw before, doesn't it? No one says anything, so I'll take that as yes. Yes. The difference here is that we don't have a connection as we did before with TCP, so we don't have this connection tracking, we don't have a client and a server socket in that sense, we just open and maybe listen and maybe send. That's kind of up to us. That's the whole thing with UDP, we're just like, let's see what happens. So we make a new UDP socket, we tell it that it's an INET 6 socket, which is a Internet 6 socket to, yes, not really what we, let's just call it an Internet 6 socket. Then we bind it to the address and the port of what we want to do, want to listen to, and we can then loop over as we did before and say, hey, receive some data, it's in some length. Here we'll say 256 bytes. Get some address info about the client, and it's basically the same thing. Figure out if it's IPv6 or IPv4, connect it over, write something back to the client. That's it. So just like before, and we can test it just like before by breaking this thing. Instead, Ruby UDP server. And then we can do nc-u because now we're over UDP. We can connect to localhost 4123455. I wrote that right. Yeah, I did. And then we'll write something, and great, we got a response back. Well, great. Nothing really magical about this. This is the exact same as before, just using UDP instead of TCP. Very standard. Yeah. Cool. All right. Now we get to the heart. Oh, I guess we have a client as well. Let's look at that first. We have a UDP client. It's basically the same as you saw before, but we can talk about something a second with that. It connects to an address, it sends some piece of data, it receives back from on the socket, and then it prints that message back. Not really anything magic there either. So we can run that, Ruby, UDP client. It connected. We're all happy. Okay, so far so good. Does people understand what the difference between this thing and the TCP element is? No one shakes their head, someone? Okay, cool. Now we get to the hard part, because we just talked about all these protocols that are client to server. But the internet has a lot of traffic that is not client to server, especially in your home network. There's a lot of traffic that is not client to server. In your, this is really getting funny. In DNS or bonjour, as Apple called it, but these discovery protocols, there's a lot of traffic that is not client to server. If you're, I'm right now running a, oh, let's see. Oh. Nope, that's not where I'm running it. Where was this? Oh, here. I have a Go program running here. Oh, it found a laptop. It finds all these laptops that are on my network because they just keep talking. And they send out all this multicast traffic over MDNS. So this is MDNS is a thing that's used for, like, Spotify uses it a ton. So when you take out your phone and you want to connect to, or your Chromecast, so you want to cast from your phone to your TV, the only way your phone knows where your TV is because of multicast and MDNS, because your TV says, hey, I'm Chromecast, I'm over here, you can cast to me, this is the way. And so does Spotify, and so does all these other weird smart devices you have in your home. They all use multicast, and many of them IPv6, to let you know where they are. So you can connect to them, and you can stream data to them, and so on and so forth. So this is just a sniffer of MDNS, which is DNS, but multicast DNS, so it's running locally on the network. Yeah, so just to explain that there's a lot of stuff that's just happening on the network that you're on. Your laptop is sending out a ton of data that you don't necessarily know about. Like AirPlay, great, you can do AirPlay, okay. Yeah, just to say that there's lots of stuff that's talking on the network. So now I'll teach you how to do lots of that talking on the network. We won't use MDNS, we'll do our own service discovery. This is the hard part of the talk. The code gets more messy here, so we'll take things slower, and please tell me if things are not making sense, because they could very well not be. Okay? Cool, I see nods. Great. So, multicast. So we'll need a few things here. We'll need to know the interface index of your network interface. And your network interface is called different things depending on what operating system you're on, if you have multiple network interfaces. Like if you're running Docker, that will have a network interface and stuff like that. We need to figure out what the index of this interface is, among other things. So what we're going to do is that we're going to take all the interface addresses that exist on your machine right now, and then we're going to reject anything that doesn't have a linked local address, because that's what we want to use in this example. And we're going to reject everything that doesn't have a flag set. This is an AND, so we're binary ANDing, the socket IFF multicast. So everything that doesn't have a linked local address, and everything that is not a multicast capable NIC or like interface, we're not going to look at that. Then if we pass the name to this thing, we're going to select the name, and then we're going to return the name of the interface, the index, which is going to be very important in a second, of the index, of the interface, and the IP address. And this is a linked local address. See, now things get a bit weird, because here in the Humi office, we don't support IPv6. We don't have IPv6 on the network here. So how can I communicate over IPv6? Well, what happens in IPv6 is that we can have many, many addresses on our network interface. In IPv4, you would wait for a DHCP server to give you an address, and you're like, great, I have this one. I can only use this one. Sometimes you will see that your, especially your Windows computer, if some of you have that, tries to get a DHCP address, and then you get this weird 169.254.something.something address. That address is the address designed for linked local communication, so communication only on the network link. Windows just gives that to your computer because they're like, yeah, whatever. But we can use this in IPv6. And actually what happens is that every single network interface will have a linked local address. If you connect to your AWS instance, and you look there, it probably will have a linked local address, even though you don't have IPv6 on your AWS instance, or on your home computer, or on whatever here. So even if you don't know, you're already using IPv6. It's already enabled on your computers. If you try to disable it, your whole computer is not going to be able to communicate. I think it's on the Macs that they will do all the internal communication between the programs on your computer only over IPv6. So if you try to firewall away IPv6, your computer just stops working. So it's also like, it's in many things. It's in, I think it's Tesla's chargers. There's a protocol that's running over between the charger and your car. That's also using IPv6 multicast. So it's in many places because it's really, really simple. This is why people who build hardware like IPv6, because it's simple. Yeah, so we come back to the address thing. So if I look at my Mac now, and I look at the interface called EN0, which I don't know what EN stands for on a Mac. If anyone knows, I don't know. If I look at EN0, I'll see that there is some IPv4 address down here. That's the address I got from the DHCP server, and there is a subnet mask here. This is a /20, interesting. But yeah, that's fine. Like, I get some address. I don't really care about that part. But interestingly, I also have an IPv6 address, and it starts with FE80. So FE80 is this magical space that's called the link local addresses on IPv6. The traffic that you send will never leave your network. So if I send something on this with this address, it will don't go out of the Humi network. It will not go anywhere else. It will just stay on this link. And these get configured automatically. You can have many of these if you want to. And some operating systems allocate like 4 or 5 of these. Or you could allocate 1 million if you want to. There's not enough IPv6 addresses. You can do whatever you want. But these are on every of your machines right now. They're probably also on your phone and on a bunch of other things. So that's really practical because we can use this. We can use this to communicate between devices. So that's the whole address we were talking about before. So basically, the thing that I did before is just going to figure out what is the index number of this EN0 index, and then we're going to get some info from that. Cool. Does that make sense? Or is that weird? General consensus makes sense. Cool. Well, I both got a thumbs up and 1 nod. Then thumbs up and the nod. Weird and cool. Weird and cool. Right. Cool. So now this first section makes sense, right? We get the name, which is probably going to be EN0. We get some index, which is some number, and then it's some 32-bit unsigned integer, I think. And we get some address, which is that link local address. So, cool. Then to the create socket part. Creating a multicast socket requires a bit more than creating a normal TCP or UDP socket, because we need to tell a bunch of things. First, we will create a socket like we did before, just a standard INET6 socket. We will then have to set some structs, or what in C would be structs. We're just going to give it a string that kind of represents the struct, what the struct content would be. But we're going to use set socket option here, and we're going to set the socket option for the kind of namespace, let's call it that, of IPv6 protocol of IPv6. We're going to say, hey, we want to join a group. We want to join the group that is based on this IP variable, which is the multicast address. So which destination in multicast we want to send things to. The index of our interface, that was the one we talked about before. And then we want to use the pack function, which basically takes a string that tells us how do we want these fields of this string represented in binary. Let's call it that. So here, capital I means unsigned integer. I could have written C, which meant a char, so we would just write a byte in there. And there's a bunch of other things pack does. Pack is really smart if you're trying to do binary level stuff. It's a really, really good function for that. Or if you're trying to do like payment stuff, because all the banks does weird binary formats that's not really binary, but kind of binary. And then they're like, oh, this is 3 fields long. Like, so pack would be great there. We're not using it there because we didn't write it recently, but that stuff would be great for that. So yeah, we're going to set socket option. We want to join this group, this multicast group, on this address on this interface. Then we want to tell how many hops we want our multicast traffic to go. Hops is network hops. So if I wanted it to go from here to Google, I would probably need, I don't know, 4, 5, 6 hops, something like that. That's probably where Google is compared to where we are. But we don't want it to leave the network, so we just say 1. That's basically all it says here. And then lastly, we will tell it what interface we wanted to do multicast on, which is the interface we had up here before. Then we're going to bind our socket to everything, as we talked about here, and the multicast port. So that's 1, 2, 3, 4, 5. That was a lot. Does that make a slight bit of sense that we're trying to take these C structs, but we're just giving it strings instead and then hoping that it figures out? Cool.
Just a quick question on hops.
Yes.
So definitely hops should be minimum, right? Anybody would like to keep it. So what's the significance of defining this?
So every time you get to a router, there is a field in your IP packet called TTL or time to live, or like hop count. Every time you get to a router, it decrements that value in that field. If that value is 0, that router will say, boop, trash. So if you set it to 10, then you can get through 10 routers, and then after that, your traffic will be trashed. So it kind of gives you a relation, like nearest relation of how far your data will travel. You can set it to 200, like the standard on Windows, I think is 128 for general traffic. I think it's 256 on Linux and Mac. I can't remember specifically, but that's kind of the idea of hops we're talking about here.
Right.
Cool. So yeah, it's the TTL field in the IP header we're basically setting here. It's a weirdly specific thing we have to set, but that's what it is. We'll get back to a sender thread here, and we'll do every time it does that, my screen also flares, so it's also very funny up here. We'll send some data back, but sending some data back is socket send. We'll skip this for a second because I was lazy when I did this and didn't want to do any synchronization. So it's just the and then it's like whatever. So this is just like standard send as we did before. We're over the hard part. Then there's a listener. We'll get to that in a second. And then we have a thing here that starts the whole program. The multicast address we want to send on. See, here it becomes a bit complicated because we have specific multicast addresses that are used for specific things. So if you're, for example, sending stuff that is MDNS, that has a specific multicast address that's not this one. I can actually show you what it is if I go to this program over here. Not that one. DNS. Main. That one. It's this one. FF02::FD. That's the one for MDNS. If you haven't seen Go before, that's Go. That's what I have a tendency to write in my spare time. Also, I just opened Vim inside of Vim. That might be a problem. How do you really accept Vim? That's not. I actually made a macro for that, so it's fine. I've done because I've been in this problem before. Cool. So I just selected one. I did FF02 because that's FF0 and then some number. The number in the end has a significance, and that significance is what the scope of this multicast is. That could be site local, it could be site local, it could be it has a list of 10 different of them. Generally, you'll only see 2 of the used. One of them is this one. That's really all you need to know about this. You will not remember this, you will go look this up in a table if you ever need, because that's not really a relevant thing. And then you have to have like some nice random number at the end. I just added B because why not? Cool. Again, we will list on port 1, 2, 3, 4, 5. We'll have a message length of 256 bytes. Fine. Then we will start the, what is it we do now? Oh yes, we will just get the interface name from this. That was the first thing we had up in the file, so like the whole thing was figure out if it supports multicast, figure out if it has a linked local address, all that jazz. So that's the first thing we'll do. We'll take our DB0, which we will just call it with. Then we will create a socket. We will create a socket. Cool. So create socket was this thing up here where we had to set all the groups and what do we join in the C structs via strings and just push that in and hope it works because C structs and Ruby are not good friends, but we can do it like this. So that's the second part. Then we'll do the whole send request, which was the lazy part with the sleep up there. And then there's the echo listener. So that's the last part. This is actually the easiest part, almost. We receive some data. We'll take get address info from that client. This is also what we did in the UDP example. If it's our local address that this packet comes from, we don't want to start doing stuff because then it was just the traffic we just sent to ourselves. So here we're just like, hey, if the sender of this thing is me, then I'm just going to throw this out and not care. Then we're going to write out the receive message. If the thing in the front of it has a request, very basic protocol, again, very lazy stuff here. If it starts with request, which I could have written smarter than this, but if it starts with request, we are gonna send something back to that person, whoever that might be on our network, who sent us something like this. We're gonna be like, hey, cool, I'm also here. Does that make sense? See, and this is the problem, because normally with multicast and trying to see multiple people, you need multiple people to test this. And I cannot have you all on the office Wi-Fi, because I'm pretty sure our IT guy would be really annoyed by that from a security perspective. So instead, I asked a colleague to do that. So we're just gonna go here and close this terminal and close up this program, and then I'm gonna run this multicast program. So actually, I'm just gonna clear this first so we can see more. So I'm gonna run this multicast program, and so far you can see that I started wrong. That's the first thing I see here, because it says that it's listening on interface LO0. That's the loopback interface on my laptop. That's not going to get us very far. So I'm going to break this again, and I'm actually going to start it in the correct way with EN0, as we saw before. Cool. So now you see that we're listening on the interface with FE80, 495, blah, 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 blah. And it sent a request out, and no one responded to us. That's so sad. No responses. So if I get Mark to run the same piece of code, hey, we got a request from Mark's laptop that has another IPv6 link local address. And if another Mark opened this laptop and ran this code, which I didn't give that to him, but oh yeah, I have many colleagues in my team that's called Mark. That's just we have 3 people in my team that's called Mark.
9-person team?
Yeah, a 9-person team.
You need 6 for Mark.
Yeah, I don't know. We should just all change name to Mark. We also have Matt on the team, also almost a Mark, but not. But yeah, if I broke this program and I ran it, then Mark would see the same thing. He would see, if not broke, I gave it a break, but he would see the same thing that he would get from someone on this network. He would be like, hey, I'm here. And this laptop would send back, hey, I'm here. If I do that, you won't see it because it's on his laptop, so it's not really interesting. And he did it again, hey. So that's the basics of multicast. Multicast is a bit more advanced than the other topics, but it's really interesting, especially if you're doing stuff relating to IoT. It could be that you're running something on a phone or on a Raspberry Pi at someone's home. Or even AWS uses multicast to figure out, like if you're doing DevOps, the way you figure out if you're deploying a bunch of instances, the way you figure out what number of instances in that row is you call a random multicast address, and then you get a response back. So like there's a bunch of stuff that happens with that as well. It's everywhere, and again, it's infinite, you saw there's so much traffic running. So that's the thing there. Does multicast make somewhat sense for people? I see more nods this time, that's great. Cool, it's also the most fun of them all. And actually, this is the last of the demos. So if we go back here, and I also had, oh, that's not what I want to do. I also had slides for saying UDP, unicast, and UDP multicast. That's not really relevant. But now we're in discussion and questions. So anyone have relevant or irrelevant, actually anyone just had any questions about this? Now is the time to ask. No? Oh, yeah.
Well, that's right. Having used UDP for multicast, the world heard, that seems really simple.
It seems really simple, right?
Yeah.
Yeah. And it's
pain.
That's the MDNS. That's what MDNS is doing on your local network. That's using UDP multicast.
But is it, I think it's really nice.
It's really nice.
So what's the catch?
The catch with IPv6 as a general thing, not with the UDP multicast, but IPv6 as a general is that if you want to have that on your servers and you're not maintaining that yourself, you probably have to go and talk to someone in your company that has money, and they generally don't want to give you that money. That's the business 101, right? Take money, don't give money. So you have to convince them that maybe not in the short run, maybe not over the next year you will reap that benefit, but in the long run, you're going to have maybe slightly improved SEO. You'll have clients that might feel that your app is snappier. You're going to have you might have an easier time deploying your internal infrastructure. So what the big players does, like Facebook and Google and stuff like that, they don't care about IPv4. All their internal networks is IPv6 only, and then on the edge of their networks, when they have to talk to the plebs out here in the real world, they'll translate it into IPv4 if they need to. But they generally don't want to, they don't want to administer IPv4 because it's slow, it's not good on their hardware, it doesn't perform, it doesn't scale. Scale, that's always a good thing to give to your money people. We need scale. Look at how many addresses. What people do is that they can you can have a client that connects to you, and you're like, oh, you need to connect to me securely. So they get an IPv6 address back, and then that IPv6 address is local for their session for this specific client with a token. So suddenly you can have another layer of security saying, hey, if you contact me on this IPv6 address and you don't have this specific token, you're someone who's trying to steal this session. So you can really start locking things down. You can get, again, you can have you can have a billion IPv6 addresses on the same interface if you wanted to. I'm pretty sure that Linux at least will start nagging at some point, but you can do stuff like that, right? You can start thinking about security and about connections in a completely different way than you ever did before with IPv4. And generally that's what all the network people say, but all the programmers, they don't know about IPv6, so they don't think that way. But this is where people can be creative. There's probably especially spammers in the old days who send email. They're like, hey, I have an unlimited amount of addresses now. I can just change my address every time I send an email. That's great for them. And then people started doing tracking of that stuff, and that wasn't a problem. But you can do a bunch of things that you weren't able to do before with IPv4. Yeah. Also, if you think about IoT and cars and stuff like that, we're going to have so many more devices on the internet, and 4.2 software update. And 4.2 billion addresses is just nowhere near enough for all of that stuff.
Is it enough for one person, though?
4.2 billion addresses. Yeah. So what generally happens is that if you have an ISP that gives you IPv6, you will get a /64. So that is 4.2 times 4.2 billion addresses for your home. So you can have more than 4.2 billion addresses, and a lot more than 4.2 billion addresses.
Those are self-delegated to the devices, right?
Either that, you can either have it's not uncommon to give a /64 per device also. Yeah, things are getting weird with IPv6. Yeah, the options are endless. Cool.
So how many years do you think the world will take to stop using the IPv4 addresses? Is it 10 years, 30 years, 20, 30 years? But will stay forever?
If you look at your home network and you look at the things that you have at home and you go, how many of these things are kind of old, are using a bit more power than they should, but I kind of keep them running like your Nintendo DS Lite or whatever that you still want to, that only does VEP, doesn't do VPA, that might also be a problem. But some of these old things you keep around, they will only support IPv4. So you might still have need for support for it, or you will have some kind of transition technology, a translator that will sit somewhere in between. That's kind of hard to say. I think that if you look at countries like France, 85% of traffic, IPv6. They probably have a good amount of legacy devices in that last 15% that is just whatever old device that people had at home. But some of them will, for power regulation reasons and a bunch of other things, also be obsolete in a very short time. So maybe it won't take that long. Maybe France will be over IPv4 in, let's say, like 10 years. Maybe other countries will staunchly hold on to IPv4 because that's the thing. Like, I think in North America there's an appetite to grow and to have new things. It also helps that the American government said that every government service that needs to, like if you're a provider for the US government, your app needs to be IPv6. That probably also helps. So there's a lot of incentives like that lies around security in this situation, for example. So it depends on the jurisdiction. I think, especially over the last 2-3 years, there's been a lot of growth in many markets. Yeah, but it's a good question, and it's a good question, especially because I don't have an answer, and I think if I had an answer, that would be worth a lot, but no. Yeah.
Why Go and not Ruby in your spare time?
Because I also do hardware, and Ruby and hardware are not the best combination. Unless you get it to run ASM, and then maybe you can compile your Ruby to WebAssembly, and then run that on your hardware. I don't know, maybe that's the thing. Someone probably tried. Maybe that's the next talk you'll get, someone who tries that. Cool. I think that's it.
Yeah. I'm just gonna go
Also, like there's gonna be some resources. Again, you'll get these slides, so you can check out these. I also wrote like a